This session we are going to complete the propagation of TE mode waves through a parallel plate to a parallel conducting plates. Okay, so now we have derived equations up to 13, and the equations that what we have got are going to be very important from equation number 8 to 13. So they are going to be the governing equations for us to solve for the rest of the equations. So in order to solve these equations, compulsorily we have to derive, we have to come up to equation number 13. So once we get up to 13, now by just using those previous equations, whatever that we have got, by using those previous equations we are going to solve the rest of the equations for the TE mode propagation. Now from equations 8 and 9 we have got two equations. One is going to be for electric field, another one is going to be for the magnetic field. So for electric field, what we have got now, we have got dou square E by dou x square. We have got dou square E by dou x square plus P square E equal to minus omega square mu epsilon E. That means this is the equation for electric field. Similarly, we can write equation for the magnetic field. Simply we replace E by H. Thereby we are going to get a equation for a magnetic field. Okay, now we are where these equations are written generalized case, where electric field is just generalized case. Now we expand the above equations 8 and 9. When you expand, you are going to substitute Ex for E, Ex, Ey, Ez for E, and we will write them independently. So therefore wherever you have E, we replace it with Ex. Wherever you have E, you replace it with Ey. Similarly, replace it with Ez, and thereby we normally going to get three equations which are going to be the electric field equations along x direction, y direction and z direction. Okay, or z coordinates, along x coordinate, y coordinate, z coordinates. Now we are looking for the wave equations for TE mode. What is TE? Transverse electric field. What is the meaning of transverse electric? The electric field is transverse to the propagation of the wave, to the propagation of the actual wave. Now since the TE is transverse, where the electric field is residing? The electric field is residing perpendicular to the propagation of the wave. That means along z direction, what is electric field? It is going to be 0 in the TE mode of propagation, whereas magnetic field is going to exist for the TE mode of communication. Since magnetic field is going to exist, these waves can also be called as H waves or magnetic field intensity waves. So in a TE mode wave, we normally write Ez is equal to 0 and Sz not equal to 0. Now first step is what? Whenever I say TE mode, you should keep in mind that TE means what? TE means transverse electric. That means electric field is transverse to the propagation of the wave. So since electric field is transverse, what is the meaning of transverse? Perpendicular to the propagation of the wave. So when the two waves are perpendicular, or when two signals are perpendicular, they simply come under the principle of orthogonality. So since they come under the principle of orthogonality, definitely we can say that we really cannot have the electric field. We really cannot have the electric field along the z direction. That means one wave is going like this. This is another wave. This is Hz. This is E component. Okay. Now transverse electric field. Electric field is transverse to the propagation of the wave. Now wave is propagating along the z direction. Now electric field is like this in this direction. Now since these two are orthogonal to each other, they cannot mix up. The electric field cannot mix up with this particular wave. So and hence we can say that the electric field along z direction is equal to 0. So in the transverse electric field waves or TE mode waves, the Ez equal to 0 and Hz is going to exist obviously. Why? Because if Ez is not 0, Hz has to be there. Either one of these two has to be there, propagating through a waveguide or propagating through a conducting plates. If nothing is there, no question of any field, no question of any signal propagation. So therefore in a TE mode, Ez is 0, Hz is not equal to 0. Okay, now we start with that particular thing. Now similar to the previous equation, we have got dou square h by dou x square plus p square h is equal to minus omega square mu epsilon h. Now I can expand this for h in terms of x, y and z components similar to the previous equations. Now what equations in y can be written as? Now in the above equations we have equation for y, dou square ey by dou x square plus p ey, all this. We hold on this particular equation and we start with this equation where I can write dou square e by dou x square is equal to this equation. That means it is a electric field component along y direction differentiated with respect to the x axis, because our plane, now we have, this is a solved equation. In this equation, what is the overall equation that we normally going to have? Dou square e by dou x square plus dou square e by dou y square plus dou square e by dou z square. So in that equation, dou square e by dou y square is 0. Why? We have made the y axis components as zeros. If you differentiate anything with respect to y axis or y coordinates, we made it 0 for a simplification purpose. So as the waves traveling along the y direction or y axis are going to be uniform or constant, we simply take that as 0. Therefore we left over with the dou square by dou x square component and dou square by dou z square component. So this part is going to be dou square by dou z square component, which we have got it over here, is equal to this one we normally going to have. Okay, so like the similarly we will be getting for the magnetic field with the similar grounds. So magnetic field we need not do separately. Once we get electric field, we simply going to write it directly by replacing electric field with a magnetic field component. That's all we do to fasten up our job of completing the writing the equation. Now I can expand this magnetic field expression which is dou square hx by dou x square, all these things similarly I can do. Now equation, in the above equation of electric field, we will take out the equation with a y. So now equation in y can be written as dou square ey by dou x square is equal to, now this p square ex square I will take it outside. So therefore now if it is going to be ey, I am going to have ey. So therefore this p into ey has been taken onto the RHS side. Once it is taken on RHS side, I get minus p into ey. Here it is plus e into ey. When it comes here, it becomes minus p into ey. Then what is, I will take this minus of common, p square plus omega square mu epsilon. What is p square plus omega square mu epsilon? It is taken as equal to k square, which is a constant parameter, into ey component. So therefore similarly, if I take this as some ey naught component, okay, so I can write this as dou square ey naught by dou x square is equal to minus k square into ey naught. So this is what the component we can normally write. Now I can signify them as equation number 14 and equation number 14(8). Now if you observe these equations carefully, now we are simply doing from based on the previous equations of from 8 to 13 only. Okay. Now let us start going with solving the equations 14 and 14a. Now just we'll observe here now what are the forms of this equation number 14 and 14a. They are going to be the standard differential equations of simple harmonic motion, and we write the solution of that equation in terms of sine and cos components. So finally we are going to get a sine and cos components where a1 and a2 are known as the arbitrary constants or coefficients of the sine and cos components. So this is what we normally going to get it over here. So where this ey naught, where is this ey naught now? Where ey naught is equal to a1 sine x plus a2 cos x we normally going to write, right? And now this we can just simply expand now here as, what is ey naught? Ey naught means what? How I can write ey naught? Because ey is equal to, what is the equation we know? Ey is nothing but equal to ey naught into e power minus pz. Why? Because we have to represent the wave which is there along the z direction. Therefore we are simply multiplying it with e power pz, where p is the propagation constant and z is the axis of the wave propagation. So from this I can get this ey naught component, as Ey naught is equal to simply Ey by this factor. Now I simply replace this factor over here to get into this. Now after I get this, I can write this equation Ey as equal to this component into e power minus pz. Now here at this time now we apply the boundary conditions. What are the boundary conditions we have taken in the very beginning? So you have to consider the figure that I have drawn in the beginning class of this wave equation for in the conducting medium. So what is that beginning thing which we have taken now? We have taken a sheet of conductor along x is equal to 0 axis and another sheet of conductor along x is equal to a axis, and that is expanding infinite distance over a z direction. Okay, so that is what the sheet we have taken along x direction. So that you have to imagine. Now there we have assumed some boundary conditions. What are the boundary conditions? The tangential component of the electric field along the internal walls of the conducting plates is equal to 0. So therefore we will take E of t is equal to 0. If you see here carefully, E of t is equal to 0 at the surface of the perfect conductor for all z and time period, for all z axis and the time period for the signal, because signal is varying with respect to time. So from above figure, that means the starting figure whatever we have given, we can write x is equal to 0, x is equal to 0. At x is equal to 0, what is Ey? Ey is also going to be equal to 0 at x is equal to 0. So therefore this Ey component is taken as equal to 0 at x is equal to 0, because at x is equal to 0 the wave is the Ey component is equal to 0. No, there is no component along Ey along, there is no field along the y axis. So Ey is equal to 0, and I can just substitute the same equation over here as a1 sin kx plus a2 cos kx into e power minus p into z. So in TE mode, sine part is going to remain and cos part is normally going to get eliminated in this equation. So for a TE mode propagation, remember, for a TE mode propagation, the sine component is going to remain and the cos component is going to get eliminated. This is very important. TE means what? Transverse electric field, which means what is the actual energy which is contributing for the wave propagation? It is the magnetic field, not the electric field, because electric field is transverse to the propagation of the wave. So the magnetic field is propagating. That means sine part remains, cos part is normally going to get eliminated. So now it is something like even function and odd function, right? So TE is something like a odd function, TM is something like a even function. In TE mode, actually electric field is going to contribute for the propagation of the wave. In a TE mode, what is this? Magnetic field is going to contribute for the propagation of the wave. This is what very important for us. So therefore the EE component I can take as equal to 0, sorry, A2 component I can take as equal to 0. When A2 is 0, what I can write now? Ey is equal to A1 sin kx, k suffix x into e power minus pz. Now in this equation we will make A2 equal to 0 because cos component is not going to be there. So therefore I can write Ey is equal to this factor in terms of sine. Now on a sheet of conducting plates, at x is equal to a, we put Ey is equal to 0, because along y quadrant, along y axis, we are considering all the fields are going to be uniform. So therefore when you differentiate that value should be equal to 0. Therefore we will consider the electric field along y axis is equal to 0. The electric field is going to exist only along x direction, if at all there, on the z direction, but in the z direction anyway it is not there. So the electric field component is going to be there only along the x direction here in this particular case for TE mode of propagation. Now, so now in this condition what we are going to have now? At x is equal to a, that means at x is equal to a, what I can have now? This part Ey is equal to 0, I can write a sin k into e power minus pz, e power minus pz is 0. Now sin Ka is equal to what I can write? Is equal to 0. Now by solving this equation, this Ka can be substituted for m pi by a, where m is going to take different values like plus minus 1, plus minus 2, plus minus 3, plus or minus 1, 2, 3, 4, so on. They are called integers. Now m is not going to be 0, because if m is equal to 0, Ey component is going to be 0 for all x and z. So this Ka component I can write as equal to m pi by a. Okay, now by solving this, now by substituting this equation, what I can get now? Ey is equal to a1 sine kx means what? m pi by a into x, m pi by a into x into e power minus pz component we normally going to get. So that means here what is variable here? Here x is variable for us, because the sheet is varying between x is equal to 0 to x is equal to a. The conducting plates, there are two conducting plates, one is at x is equal to 0, another is at x is equal to b. So therefore the variable thing is going to be x quadrant, therefore this sine component is going to vary with respect to x. Okay. So now Ey is equal to a1 sine m pi x by a we normally going to get into e power minus pz, and that equation can be written as say 15, equation number 15. Now we will differentiate that equation dou Ey by dou x. So once we differentiate, what is the answer we are going to get? Once we differentiate, what is the answer we are going to get? Dou Ey by dou x is equal to differentiation of sine is cos. So cos m pi x by a, what is the factor inside? That will be coming out m pi by a into e power minus pz. So that is the equation we normally going to have it over here. Okay, well, after differentiating the equation Ey with respect to x component, we normally going to have what? We will try ourselves towards going into solving for the final equation for the TE mode wave propagation. So in this now, from equation 1a, as I tell you, starting from beginning we have to keep these equations with us, because once we get up to equation number 13, that's it is only going to be substituting one equation into another equation to get into the final equation, that whatever we want. So therefore let us start with equation 1a. We have just solved this equation 1 and we got this equation 1a, where I got the equation p into Ey is equal to minus j omega mu hx. So from this I can get the expression for hx, because what is the TE mode? In TE mode we know what is TE mode. TE mode Ez component would be equal to what? 0. Ez would be equal to 0. Why Ez is 0? Transverse electric field. In a transverse electric field, the electric field component along z direction would be equal to 0. Why? Because the electric field is already transverse or already orthogonal to the propagation of the field along the z direction. Therefore this component is 0. Now next, what about hz? Hz is not equal to 0. There exists a hz component. So therefore we should try to get expressions for the h. H is very much important for us to get the equation. So therefore try to get in terms of hx here. So hx is equal to, now I can just have this minus p by this factor j omega mu into Ey component. I can normally going to have it over here. Now using this previous equation, okay, which is what called what is the previous equation that we have got now? We have got a previous equation for Ey. Ey is equal to sine component, sine of m pi by Ey is equal to, what is that we have got there? Sine of a1 sine of m pi x by a into e power minus pz. So that is the equation which we have got for the Ey, right? So for hx, already Ey is known to me. Ey is already known to me. So therefore that Ey whatever I have got, equation number 15, that equation number 15 I substitute here. Now minus p by j omega mu remains as it is. This Ey I replace with the equation number 15. So this is going to be equation for hx. Next, let us look into the equation for hz now. For hz, if you revert back ourselves to equation number 3. Equation number 3 we have already derived. Okay, we already derived. Dou Ey by dou x is equal to minus j omega mu hz. We already derived this. So from this we can get the hz component. So this Hz is equal to 1 by this factor will come onto the LHS side, 1 by j omega mu dou Ey by dou x. So this is the equation we are normally going to get. Now Hz is equal to, what is that we have, minus 1 by j omega dou Ey by dou x. So 15 equation number 15. After that we have got one more equation which is differentiation version of the equation number 15. So once you differentiate this sign, you are going to get cos obviously. So cos m pi by a into m pi by a e power minus p into z, and this factor remains as it is. This is going to be the equation for the Hz component. So after we get all these things, now we have got all the components to finally represent for a TE mode wave equation. So what is the TE mode wave equation representation now? We just mentioned that Ez is 0. Since Ez is 0, already we have developed an equation for Ex. This Ex we have got in terms of Ez, dou Ez by dou x. Okay. Now since Ez is 0, definitely Ex component is also equal to, will also become equal to 0. Therefore, we can write Es is equal to 0 since Ez is equal to 0. Ex component is gone. Ey component, already we have derived the expression for Ey. We can write as it is the Ey component, a1 sin m pi by a e power minus p into z. That means you normally going to have a sinusoidal variations here, right? Then next Hx. What is Hx? Already I have Hx here. I will represent Hx as it is over here. Then next, what about Hy? See Hy. If you remember if you go back to the equation for Hy, already we derived this Hy equation also. Hy equation we derived in terms of dou Ez by dou x. So dou Ez, this is dou Ez, I am sorry, dou Ez. This is dou Ez by dou x. So this Ez is 0 because it is TE mode. Ez is 0. Because Ez is 0, definitely this Hy is also becomes equal to 0. Therefore, Hy component is also going to be equal to 0. What is Hz? Hz already we have defined. So that means we have to get equations for Ex, Ey and Ez. What is Ez? Ez is anyway 0. In a TE mode, finally we write for TE mode. Finally, we write for TE mode. In TE mode, Ez is equal to 0. Directly I can write Ez component is simply equal to 0 in the case of the TE mode. As Ez is equal to 0 in the TE mode, we have got now all the components. We have got Ex component, we have got the Ey component, we have got the Ez component. Similarly, I have to get the components for Hx, Hy and Hz. So I got all the components, all the electric and magnetic field components along y quadrant, x quadrant and z quadrant. Similarly, I got some magnetic field components also I got appropriately. Now since I got all the field equations along the respective axis, now these are the field equations for a TE mode propagation. So once after we get TE mode, now see, observe carefully what are the what is that we can compare, how is that we can compare this. See here the components now along Hz, the wave is propagating along Hz direction. So along Hx there is a wave which is sinusoidal in nature. Along Hz there is a cos. Means what? There is a differentiation of sign is a cos component. Okay. So there is a orthogonality lies over there. There is a inclination lies over here. Hx is propagating in one direction. Hz is propagating in another direction. If they are propagating in same direction, you should get same sin or cos. So since we got a different thing now, we have to say that Hx is, the angle of Hx is different, the angle of Hz component is going to be different. Why? Because they are separated by the sin and cos. Okay. So this is what, next one is going to be Ey component, electric field component. What is important is magnetic field component. If you observe this carefully, the electric field component and a magnetic field component both are opposite to each other. That means, both are orthogonal to each other, perpendicular to each other. That is what we normally going to get it over here. And lastly, finally, similar to the above expressions, we can write for TM waves. What is Tm? Transverse magnetic field. In the case of transverse magnetic field, what is Hz? Hz becomes equal to 0 and Ez will not be equal to 0. Now how can I say Hz component is equal to 0 for the transverse magnetic field? What is the meaning of Tm? We should understand. That means what is Tm? Transverse magnetic. The magnetic field is transverse to the propagation of the wave. So that means there is no way that the magnetic field will mix up with the wave propagating along z direction, because both of them are transverse, orthogonal to each other. The wave and H field are orthogonal. Therefore, along the propagation of the wave, the Hz component is equal to 0. Therefore, H suffix z means what? Magnetic field along z direction in a Tm mode is equal to 0. And what about the electric field component along z direction? Yes, electric field is normally going to exist along the z direction. So this is what a TE mode. Since electric field is not equal to 0, we call these waves as E field waves. Okay, TM mode waves are E field waves. The name is going to be same for both. Okay, synonyms are going to be TM waves or electric field or E field waves. Okay, this is what we can normally have. Now as far as this is concerned now once again we have to go back to the previous equations from 8 to 13 and we have to solve for getting the TM mode equations. So equations up to 13 are generalized equations for TE as well as for TM mode wave equations. After that, based on the conditions, we apply those conditions and we solve for the equations. From the generalized basic equations, we normally going to compute that. Okay. So when you compute that, what is the first and the foremost thing we can write for TM mode? In TM mode, Hz component is equal to 0. In TM mode, Ez component is not equal to 0. Ez component is not equal to 0. Ez is going to exist because it is going to be E field waves or E waves. Whereas in TM mode, Hz is equal to 0. So this is what the TM mode configuration. In TM mode, Hz is equal to 0, Ez is not equal to 0. This is what we have to start with. So wherever you have this Hz, there we normally going to have a 0 component over there. So for Ey component, so in order to get Ey component, we have got Ey equation. So Ey equation in terms of H. So similar to previous thing. What is the similar to previous thing? See, this is similar to previous thing. If it is Hx, what I can have here, Hx is equal to minus P by K square dou Hz by dou x I can write. So since Hz is equal to 0, what I can write Hx as? Hx becomes equal to 0. Therefore, I can straight away write Hx is equal to 0 in this particular equation. Anyway, Hz is equal to 0, Hx also I have got. Now last remained is going to be simply Hy. Now to write Hy equation, what I can have now? It will be simply other than the Ey component. In Ey component, if you got sine, in Hy component you are going to get cos. So by looking into Ey component, you can write Hy component as cos component. So I will be getting the Hy component here. Similarly, what about for Ex component now? Ex component. What is Ex I can have? So when I solve like that, similarly I will be getting the Ex component. So Ex is equal to Pa by j omega this cos m pi by x. So for Ex component, Ex is similar to Hx. See, Ex and Hx both are almost all similar except sine and cos. Here you will be having sine for Hx. In Ex you will be having what? Cos. Rest of thing is same, m pi x by a. Now here you get a difference here because you are writing here for Hx. Therefore you get a j omega mu. This is for Ex, so therefore you get a j omega epsilon. This is the difference that you have to remember when you normally going to solve. Okay. Then after this, you are going to have final component is Ez component. Ez component means what? By looking into Hz component, we can write the Ez component. See this here, minus 1, 1 means it's a constant factor, some a1. You can have this is a1 actually, this is a1. So minus a1 by j omega mu. Similarly minus a1 by j omega epsilon I can write. Into cos factor we get, the cos is replaced with a sign here, where we normally going to get the Ez component. So therefore in the exam, if at all a question has been asked to derive the wave equations, propagating through a parallel conducting plates for TE and TM mode, both if at all you got a question, then what you should do? Simply derive the equation for TE mode up to come up to here, and by small variations that you have just now I explained how, right? Based on that you directly write the equations for TM mode also. Okay, now for TM mode I can give you as a homework, right? You can take this as an assignment and you can submit it to me. After you complete TM mode, I will send you the appropriate material for this wave propagations. You can just refer that reference thing and you can send it to me. Okay, so with this we normally completed the first unit equation part. In first unit, what is that we are going to have? We have wave equations propagating through a parallel conducting plates, right? So this is what we have completed, our first unit part. Next part we normally going to have some wave velocity and problems on the these conducting plates. So after we complete these two topics, we will be completing the unit number 1. Okay, so after we complete unit number 1, then we have to go back. That means same kind of equations we normally going to solve, but for the waveguide. So we normally going to consider a waveguide and we normally going to solve the same equations for TE as well as for TM mode wave equations. After that, in second unit we are going to have once again problems on that particular TE and TM mode wave equations. So we will solve for that. Okay? With that, second unit also going to get completed. So only first unit, second unit is normally going to have all these derivations. After second unit, the life becomes easy. Only you are going to have theory and very small problems that you are going to have in the microwave techniques subject. So if you practice unit number 1, unit number 2 equations, then the subject is going to be very easy to pass in the end examination. So for today's class, we will stop it here. Thank you very much. You can just see it for a quick reference.